Thank you very much. It's my real pleasure to be here, especially following some of the amazing talks that preceded me. So my name is Richard Murray, I'm Chief Executive of Orca. I thought I'd start with a quick background to myself. So I've spent my career in and out of technology. I have a PhD in quantum, but in 2013, I was brought into the UK government to help launch the UK's program in quantum. And I just want to remind people that in 2013, no one was talking about quantum. So it was a fantastic time to be inserted into that community. And since then, we've seen the explosion of interest and real deployments and technology progress in and around quantum. So in and out of different public roles and company roles. And then in 2019, I was one of the co-founders of Orca. So let me just say, what is quantum? So one of the previous talks really nicely elaborated on what quantum is. At this point, based on that, I would just say that quantum, it's not a new technology. It's not even a few technologies. It's a new way of looking at data. It's a new way of going back to basics and processing the very thing that the very heart of what we think is. It's a new way of looking at data itself. And what this means is that it's not just computing. It's a whole plethora of new technologies that collect data, that communicate data, and process data. So let me leave you with this one point. It is not one technology. It is a suite of technologies. It's a new way of looking at data. And what that means, and again, the previous talk elaborated a lot on this point, is it is a new, hugely exciting range of potential capabilities. So with quantum, you can revolutionize the way that you look at healthcare. So non-invasive brain measurement is only possible with quantum. We can control computers through our thoughts. It's a new way of looking at infrastructure. You can see beneath the ground. You can monitor oil rigs without touching anything, purely based on looking at gravity signals. And there's a new way of navigating. So no longer do we need to rely on satellites to move from A to B to guide us. We can rely on inertial methods to determine our position. So in each of these three areas, you can see a new, completely fantastic new capability and a new potential to revolutionize the way we do things by harnessing quantum data. But of course, I'm here to talk to you about quantum computing and what that can bring. Quantum computing is probably the first paradigm shift in computing that we've seen for many decades. For a long time, we've been focused on zeros and ones, semiconductors, silicon. That's been fantastic for us, and of course, we've seen the explosion of AI because of that. But now it's time to relook at what computing is. And quantum computing is really the first reinvention of computing itself to help us address these huge challenges that we face. So quantum is a new way of looking at computing that will align with our current models of computing. Many people are familiar with this image. This is the standard image of a quantum computer, a cryogenically cooled superconducting qubit system. I love to say to people, this isn't the only model of quantum computing. So you've seen outside the Pascal stand, very different way of looking at a quantum computer that doesn't need cryogenic fridges. Orca as well is developing photonic quantum computers, which can be contained within a 19-inch rack. So there is no standard model of quantum computing. It is a rich and very innovative field with many different types of technologies. So this is our PT1 system. This is the system that we've installed with Neom to be using to advanced applications in machine learning and optimization. So why does anyone care about quantum computing? I think it's really interesting to look at the potential first applications. And there are many, but these are the three that I think are the most interesting. I think as a starting point, using quantum computers to change the way we discover new materials. So it's fantastic to think that we actually don't understand how some of the most powerful natural molecules, we don't understand how they work. We don't understand how the blood can absorb oxygen. We don't understand hemoglobin. We don't understand how plants can harness sunlight to produce. We don't understand chlorophyll. We don't understand high temperature superconductors. These materials are completely unknown to us, completely outside of our current computational abilities, because they're quantum. So firstly, we can start to really, truly understand and design these amazing new molecules. Secondly, many people are challenged in terms of how well they can optimize and search through data. Quantum, because of the way it's able to parallelize the search for data and information, can revolutionize the way we can search through data. And then finally, and in my view, the real bleeding edge of what people are doing is the inclusion of quantum within future machine learning and generative AI models. So you can really look at adding quantum into those existing models to make them better. So I thought I'd just elaborate on that last point just slightly by giving a great case study of generative AI as it's currently applied to chemistry. So, by the way, this is the second fastest growing area of generative AI, the use of generative AI to predict new molecules. All companies are looking at this, but it's really limited. So the total number of molecules that you can predict with a current generative AI model is about 10 to the 80. Huge number of different molecules. But the total number of molecules that it can possibly exist is more like 10 to the 180. So if you look at these numbers, there is an order of 10 to the 100 potential molecules that can exist, which we are not accessing currently with generative AI models. One very interesting example of this is when you look at snakebite. So if you try and find a solution to snakebite venom, the solutions exist in this area of 10 to the 100 possible molecules which cannot currently be modeled. So there are real therapeutics which are not currently being discovered because of the limits of our current computational capability. Quantum can change all of that. So a little bit of a technical slide. When Orca looks at applying, and this is not just unique to Orca, when companies look at applying quantum to existing generative models, what you look to do is, as David Keyes was saying, include quantum alongside classical high-performance computing, but really at the bleeding edge, inclusion in those models to drive much better outcomes. So what does the future look like? Especially what does the future look like for some of the fantastic activities here in the kingdom? Many people are aware of these things, these AI factories being built. They are hugely exciting, especially when we consider what we can do with them. But there's a probably hidden, or maybe not so hidden fact about the huge challenge in installing and continuing the use of these systems. So these systems consume something like 64 megawatts of energy. Each megawatt is about $1 million a year. So to install these systems is one thing. To continue to run them comes with an energy cost of something like $64 million a year, just the energy price alone. So this is incredibly exciting, but can we do better? Can we include quantum into these AI factories to make them better, make them more energy efficient, make them more performant? The answer is probably yes. So here's a silly illustration, but you can imagine a quantum computer of many types, including Orca, being embedded within these systems, being a permanent home within these future AI factories in order to lessen the environmental impact and do more with the limited GPUs or limited energy that we all live with. So this, in my view, is the future of high-performance computing and also the future of quantum. Okay, let me just pause for it and be slightly more technical now. There are, of course, huge challenges in building a useful quantum computer. I list here just some of the challenges associated to building what people commonly refer to as a large-scale or error-corrected quantum computer, which is essentially being very good at being able to both create very high qubits and also control them at the same time. So there's a long list of you need very high-quality qubits, you need very high-quality operations, all the way down to much more practical but still very real impacts, like you need very fast classical processing. You need a big high-performance computer. You also need to be very much looking at how you can develop the right components to be mature, and also delivering these systems at a reasonable cost and value. So it's no surprise that quantum is fantastic. We're all really excited about it. Let's also remember that this technology is not easy. It's taken 100 years to get us to this point, and we're only just at the cusp of making these systems practically useful. So this is a picture of the inside of, I believe it's a Google fridge, dilution refrigerator. This is a tough challenge to solve. And these systems are currently big, bulky, expensive, low maturity, with some unlimited applications. But if that scares you, it shouldn't. What you should be thinking at this point is, this is coming back to the original dawn of computing itself. This is a picture of the bomb machine, the machine designed by Alan Turing in the 1930s. All of those challenges that I mentioned most definitely applied to this system at the very dawn of computing itself. And of course, now we know that computing is available and easy, but those problems have been addressed to get us to this point. So there are challenges, but of course it is very straightforward, very real for us to be addressing those challenges, especially within a vibrant ecosystem such as this. So I thought I'd start to end with just some of the choices. So unfortunately, quantum computing still has many variations, many different ways of approaching it. If you're familiar with quantum computing, I'm almost certain that you'll be familiar with the choice of which qubit is best. I actually think it's a bit of a sort of moot point, a bit of a silly point. Every qubit is good for a certain application. But there are certain choices to make in terms to decide how to apply quantum, which qubit is best, whether you are concerned with fully quantum or hybrid quantum solutions, whether you want a system which is on-premises versus a cloud solution, how long you're willing to wait, what the timing of your solution, what the timing that how long a horizon you're looking at. And finally, whether you really want a fully quantum computer or how much you're preparing for embedding quantum with classical solutions. So this is a slide to illustrate the choices, the different variations, but also the richness of innovation that's currently happening at the bleeding edge, at the cutting edge of quantum research within companies and within governments today, right now. So I thought I'd end with just the state of play at the moment. So the global quantum industry, the global quantum community is ballooning, it's exploding. So not only are we seeing the emergence of the very first industrial use cases for quantum, which by the way are a pipe cleaner for everything else that will come after it, we're also seeing the rapid evolution of the hardware to be making it more performant, but also more practical. And finally, the number of applications that we're seeing are growing year on year. So it's no surprise to see that the global ecosystem, the number of companies pursuing this is growing at an equal rate. And I'm excited to be here, quite frankly, because I think mapping that potential capability to an exciting and emerging economy in the Vision 2030 that's happening here today is one of the solutions to unlocking some of the first applications of useful quantum computing in industrial applications. So that was a very quick whistle-stop tour through everything. I hope that's been useful and look forward to talking to you all today more about that. Thank you very much.